Hello. Hello. So, welcome to the final episode of Differential Amplifiers. After this, we will move on to output stages. But before then, let's look at this very interesting concept. Up until now, we know the differential amplifier looks like this. It takes a differential input and gives out a differential output. But what if the next stage in the circuitry allows only a single-ended input? Obviously, we cannot just short circuit these outputs and join them here. It wouldn't work that way. So let's go inside the differential amplifier and see what realistically we could do. So I'm going to draw another differential amplifier here. Okay, so previously we've known that we could just put a current source on top of this. I'm going to do that to get more gain. Okay. All right. So what we are looking at is when we need to feed the next stage with a single-ended output. If we feed only this side, then what happens? We are going to get a distorted output, which is not desired. Then the whole purpose of differential amplifier is defeated. Okay, so that would not be so helpful. So what in actual sense we could do is this. So we place a current mirror right on top. Okay. Then connect this to another P-type device. So the bases are connected, but clearly we can see we've lost symmetry. Okay, so we have our V in 1 here and our V in 2 here. Then we are going to take our output from here. Alright, so we are going to take the output from this side alone, and we are going to prove that indeed the gain we are going to get is not going to be half the circuit, half the gain of the original circuit that we had. It should be exactly the same as the gain of the differential pair. That's what we are going to look at. Alright, so what happens is previously, without this setup, we are only going to get gain for half of the circuit here. So whatever happens to this part is not affected because we are taking the gain from only one side. And you can prove that taking the gain whilst it's connected as a, now this is a tricky one you need to understand. Even though we said the differential gain is the same as half circuit gain, but if we connected it this way, the gain we are going to get from this single output is going to be half the differential gain. So if the differential gain is supposed to be minus GM RO, taking the gain from only this side is going to be half of that. Okay, it might be a bit confusing to understand, maybe not to keep this video too long. Probably there might be another video for you to fully understand why this is so. Might be confusing at first, but you could just simply understand it this way, that the differential gain itself is giving me negative GM RO. That means Vx minus Vy. So if Vx minus Vy is giving me something, now remember why it's like that, because if we remember the intuitive view, Vx is an output that's going this way and Vy is an output that is going this way. So the difference will be an output that starts from here and there. So all this is giving us negative GM RO. Then if I took only this, or without a minus, only this as the output, I'm going to get an output which is only this big, and that is negative GM RO, but only half of that. So you can just think of it this way before maybe later we can prove it mathematically. Okay, so that's a drawback we don't want. So how do we feed our differential output to a single-ended stage at the next input stage without losing the gain and also the noise cancellation? So we are saying we place a current mirror, as we know before, here, and we feed it onto another PNP device. Then we take our output from this side, and this is called an active load. So we are going to do the analysis and see what happens in this our setup. Okay, so assuming there's a change in voltage here, so V in goes up, then what happens to the current? The current has to also change. So there's a change in voltage which rises. It means that VB in 1 has to rise by a small change, which would also cause a small change in current here. Okay, and the rise in current will mean that the voltage generated at this point will rise, and since this is used to bias this Q2, call them Q1, the voltage here will also rise as the base emitter voltage or emitter base voltage would rise, and that will cause more current into this side. So I'm going to draw the small signal analysis of this half circuit, which looks like okay. So in the small signal analysis, since there's a change in voltage here, we are seeing this as the input So this Q2 here is taking some input signal in the form of change in voltage, and we know where that change in voltage is coming from, and that means we are taking our V out from here, and we are seeing this Q3 in small signal analysis as just a resistor RO3. So assuming there is a change in voltage, which is a rise in voltage, because our analysis here is from a rise in voltage, then what happens is the current through this side should also increase, and increasing the current into this node and to this resistor as seen means that we are going to have a slight rise in voltage at the output. So assuming there's current going into this node and there's a resistor here, a small change in current, that means we are going to have a rise in output. Okay, so take your time, make sure you understand this very well. All right, then we look at another scenario when the input, so because the inputs are differential signals, when this one rises, we expect this one to drop equally because they are differential signals. That's why differential signals were explained in an earlier video. Okay, so analyzing this half of the circuit during that scenario, what happens when, so I'll just redraw the circuit this way. So this time around, this side looks like a transistor taking a signal, and this guy who is not taking the signal will just be seen as a resistor. Okay, so we are going to make it look something like this. Q2 now becomes RO2, and this is the same V out. And this time around, the change in signal here, the differential input, is such that when the input at the other side is rising, which we've realized that it will cause an increase in the output voltage. When this one goes up, this one should go down in equal amounts. Okay, so what happens is that if we have VCC here and this voltage is going down, the VB in would also have to go down. So VBE2 would also have to go down. And if VBE2 goes down, then what else goes down? The change in current goes down. And if the change in current goes down, it means that the change in, or the change across the resistor R2 also goes down. And once the drop, the voltage drop across resistor R2 goes down, and if the drop across R2 goes down, what happens in common emitter stage is that the output here would go up, because the output should look like VCC minus change in IC over RO2. Okay, so once this voltage, this current drops, then the voltage drop here will drop, and we are subtracting a smaller number from VCC. It means V out would go up, and that sort of complements what happens before. So looking at it carefully, now two things are happening. Let me redraw. So by connecting a current mirror here, PNP current mirror. Oh. Okay, so by doing this and our output taken here, when there's a differential signal, which means as V in 1 is going up, differential signal V in 2 would go down by equal amount. We just discovered that this going up, V in 1, so let me rename them Q1, Q2, Q3, Q4, causes a raise in voltage, output voltage, by a certain amount. Obviously by the same amount, which is going to be GM1 and its appropriate output resistance impedance times V in 1. Okay, so that's by an output, so don't let us confuse ourselves by that. Okay, and the same way, a raise, so when this one is increasing, it causes the output voltage to increase, and when this one drops, we just did the analysis earlier on, also causes the output voltage to increase. So the reverse, when this one goes down, it will cause the output voltage to go down, and when this one also increases differentially, as this is going down, this will go up, it will cause the output voltage to go further down. So this means we can have a single node having that doubled gain, because the two effects of the output will double up, and the two effects of the output also double up in both scenarios. That means by doing this connection, which is called an active load on a differential pair, we can have a single-ended output which has the same gain as the differential output, and the gain is going to be the same as we've done before, RO, or whatever output impedance that we will have. So we'll try this on LTspice in another video. Until then, take care. Bye.